Welcome to the High Energy Density Science Center seminar series. Today I'm happy to have with us Dr. Madison Martin. Madison is a design physicist that supports the plasma science W81 and W84 programs. She currently serves as the design lead for the Orion campaign, which uses short pulse lasers to heat buried layers for an emission-based opacity measurement. Madison received a bachelor's with a dual concentration in physics and mathematics from a small liberal arts college embedded in Florida Atlantic University. She received her PhD in nuclear engineering from the University of Florida in August 2017. Prior to that, she spent 3 years as a Livermore graduate scholar at Lawrence Livermore National Laboratory, where she completed her thesis research designing a short pulse laser-driven opacity experiments. Madison enjoys engaging in broader lab activities, such as participating in interviews, recruiting events, focus groups, strategic planning discussions, and STEM outreach activities. Outside of her scientific endeavors, she enjoys spending time with her husband and 2 pets, a cat and a dog, as well as hiking, dancing, running, and reading. I'm looking forward to her talk on opacity, and I want to make sure everybody understands that today's talk is an unclassified open meeting, so please be aware of that. And also the talk is being recorded, so if you're uncomfortable with that, please log off. And otherwise, if you have any questions, you can enter them in the chat field and I will read them at the end. Or if you want to ask your question verbally, just put like a Q or something in the chat and I will call on you in the order that things appear in the chat field. Otherwise, please take it away, Madison, and sit back and enjoy. Thank you.
Thanks, Paul. Seems like you can hear me okay. I see I'm getting boxed in as I'm the speaker, so thank you for the introduction. I'm here today on behalf of the Orion team, and I'm going to talk to you about stellar relevant emission-based opacity experiments at the Orion laser facility. But first things first, I wanted to point out that our Orion team, there we go. Our Orion team is a large interdisciplinary and international team. So the experiments take place at the Orion laser facility, which is located at AWE, or Atomic Weapons Establishment in the UK. And the PI for the experiments is Dave Horty. And there's also been some collaborators that we've worked with regards to data analysis, modeling, and theory with AWE as well. And then here at Livermore, we have quite a large group with 3 main components, which I've tried to color code. So Greg Brown is our group PI, as well as the experimental lead for all of our campaigns. All of the other experimental support team members are in black, and Mark Ford is our theory lead for this Orion effort, and all of the theory group members are in blue, and then I'm the design lead, and all of the design team is located in green. At the very bottom, Bob Peter and Heather Whitley are our programmatic management. So we're a large group, multiple backgrounds, and we communicate and leverage our international colleagues as well. So to give you an outline of the talk, I'm going to talk about the motivation for why we're interested in doing these type of experiments, and to explain the general platform, the experimental platform of using short pulse lasers to do opacity experiments. And then I'll give a little summary of the recent Iron campaign, which was actually a campaign we used to do a quite extensive body of work to support a milestone last year. And because I am the design lead, I'm going to focus mostly, most of this talk on the modeling approaches, which are our 2 main approaches. We use radiation hydrodynamics modeling, and we also do atomic kinetics and radiation transfer calculations. And at the very end, I'll talk about our current and future work, and I kind of give you an idea of how the modeling work fits in with the other experimental and theory groups as well. And the summary I'll probably just put up for you guys to see in the background, and at that time I'd like to take questions about the content. To start, we're interested in looking at opacity because it's an important physical property in energy transport of high energy density systems, and we really require experimental validation of opacity theory. So in a lot of our design calculations, we use energy transport models that rely on material opacities that are either theoretically calculated in line based off of formulas or are leveraging existing tables that were calculated using opacity theory. With our HED systems, we have a large range of ionization stages and can be quite complex. And so a lot of the theoretical calculations require some sort of statistical methods. And that is part of the reason we're interested in doing experimental validation of these opacity theories at these very high temperatures and high densities. I don't know if this group has heard of these experiments before, but there has been, it's been, kind of a decade plus at this time, but about 2005, there was some disagreements brought up between solar observations and solar models that were suggested could be mitigated if you increase the opacity of some key materials. And well, one example material would be iron, so metals in the sun. And there's been some experimental campaigns at different facilities to try to validate those type of materials at the similar conditions of the sun. On the right-hand side, I have a plot of the electron density versus temperature for the sun, starting at the surface of the sun at the lower left. If you follow the black curve along, that's the conditions you would reach going from the surface in the lower left to the center in the upper right. And a lot of these disagreements were looking at the transition area of the convective to the radiative zone of the sun. And there was some really great work by Bailey et al. At Sandia National Lab on their Z facility. And in 2015, they published a Nature paper that measured iron opacity values of 300 to 400% larger than predicted. And they were at conditions represented by those blue squares on that plot. And so conditions near what we see in the convective zone of the sun. So for short pulse lasers like Orion, you can get to higher temperatures and higher densities indicated by both the yellow square, which is kind of right at the transition region from the convective to the radiative zone, but then even deeper. So the red region represents even higher temperatures and higher densities that we can reach using short pulse lasers and, for example, at the ones at Orion Laser Facility. So this is usually like hundreds of EVs to a tenth to solid density. So pretty high temperature, pretty high density. The platform in the concept for using short pulse lasers is that you would have a buried layer target where your material of interest is in the center. In this case, I'm using iron as an example with some type of dopant material mixed in. So our campaign looked at sulfur, chlorine, and potassium. And then on the outside of your buried layer, you have some type of low Z tamper. And this is either usually some sort of plastic. On one side, you hit the target with a short pulse laser, and what it does is it creates a source of hot electrons at the surface, and those hot electrons transport through the target, heating these materials to these high temperatures and high densities, and causing the materials to emit X-rays. And what you want to measure is both the dopant emission and the material of interest emission on X-ray spectrometers. And in this diagram, I have one X-ray spectrometer, but in actuality, we look at using as many X-ray spectrometers as feasible. We look at time integration, we look at time resolution as well. And so the concept here for how you would get an opacity from this emission-based platform where you're measuring the X-ray emission is you use this inference equation that I have on the fifth bullet. And that inference equation is actually the solution to the 1D radiation transport equation, assuming a local thermodynamic equilibrium. And what you would measure is the red I sub nu, which is the specific intensity of your material of interest, iron in this case. The green B sub nu of T is actually the Planckian function, which you can calculate from the inferred temperature of the buried layer material. And you would get that inferred temperature from the X-ray emission of your dopant materials, which are usually heated decay shell emission and therefore the opacity theory with that is better understood. We have really good calculations. We can do detailed calculations and hone in on the inferred temperature quite well. And then at the bottom, the numerator of the inference equation, opacity inference equation, is the density times the thickness of the buried layer, and that rho delta L is usually a conserved quantity, especially since these experiments are designed to be as 1D as possible. And for our so far in our Orion campaign, we've really been focused on directly comparing our measured intensities, so the I sub nu, and also the dopant emission, and then taking those measured intensities and comparing them very directly with simulated emission spectra. So what that allows you to do is look at sensitivities to your modeling assumptions, sensitivities to what is included in the opacity theory, and you also can use things like rad hydro, which I'll discuss later, to try to understand the plasma evolution in these type of experiments. And so that's the kind of first step before you try to make an inference of these experiments. So we've been using the Orion laser facility at AWE to access these high energy density conditions. Orion is a combined long pulse and short pulse laser facility that has 10 different long pulse beams, 2 different short pulse beams, and one of the somewhat more recent upgrades is that one of the short pulse beams has been converted to green operation, and that's really important for our type of experiments. That was achieved by using 2 different independent doubling crystals, but in that one pulse beam gets to laser energies of about 200 joules. Here we have the 500 femtoseconds, but it actually, the pulse length can be extended to about up to a picosecond as well. And then 527 nanometer light in that green operation. And so with that type of laser configuration, it allows us to have access to that additional portion of phase space that I showed on the motivation slide, those high temperatures, high densities, things that are more consistent with kind of interior solar conditions. And that's in complement to both the Sandia platform at the Z facility and also the NIF opacity platform here at LL and L, which reaches sort of similar conditions to what we get at Z as well. So for our recent iron campaign, we've been using pretty well characterized buried layer targets. And these targets are, as I described before, where you have a buried layer kind of surrounded by plastic, but the way we actually build these is we use a microdot, a buried microdot. So in this top characterization, you see that there's a buried microdot of about 50 micron diameter with multiple layers, and those multiple layers are chlorine. We have a carbon tamper in there, the chlorine, potassium chloride, and then our mixture of iron sulfur, which is iron is our material of interest and the sulfur is our dopant material. And then that 50 micron microdot is encapsulated by these layers of parylene on either side. So if you were to look at it on the side, you would see what's here at the bottom, where you have your very thick tamper and then your buried layer in the center, and then you hit the target with your 2 omega laser on one side. And so here's an example of our standard laser parameters for our iron campaign. We usually use the pulse length of about 1 picosecond, energies of about 160 joules. Our focus is actually 100 microns, so we're trying to overfill that 50 micron microdot, a 50 micron diameter microdot, and that gives us an irradiance of about 2 times 10 to the 18th watts per centimeter squared. And so as part of building these targets and understanding them, we use a variety of different characterizations: proton-induced X-ray emission, electron beam, profilorimetry. And here I just wanted to include and give you an idea of an example metrology results that we get out, which we actually feed into our calculations when we do modeling, either through radiation hydrodynamics or our standalone atomic kinetic calculations as well. So in complement to having well-characterized targets, we also want to get as much coverage for our X-ray emission as possible. So we have a kind of suite of spectrometers that we field. And so this includes 2 time-resolved spectrometers, which are boxed in like the light green on the right. And those 2 look at iron L shell, which is our material of interest that we'd like to measure the, infer the opacity of ultimately, and our K-shell dopant, sulfur. We also look at 4 different time integrated spectrometers, which we use to measure more time integrated measurements of our material of interest and also some time integrated representation of temperature and density from K-shell diagnostics. And there's a wide variety. Our OREX is looking at the iron K-shell and L shell. HBS is looking at the iron L shell, and MK2 and Titan are looking at sulfur, chlorine, and potassium K-shell lines. We also field a pinhole camera GXD imager onto the microdot to see what the emission of the microdot looks like on each shot. So we try to have as much diagnostics as possible to try to understand what's happening as these experiments evolve. So as you might expect, if we're measuring a lot of emission, you have to really understand the calibration of all of these types of spectrometers. And so here's just an example of the wide range of calibration efforts that are done to understand the signals. And we really need absolute calibration for our diagnostics to be able to do a meaningful comparison and understanding of the emission that's coming off. So for our crystal spectrometers, we do them at both AWE and LLNL. So there's some X-ray tube calibration, EBIT at LLNL. We also look at our filters that we employ on the diagnostics, both at EBIT and also at AWE. We both, AWE and Livermore, we do profilometry again. And then our image plate, which is actually what we measure and record the X-ray image on. And so that's characterized at AWE using an X-ray tube with Excalibur sources. So this is a quite an intense endeavor to understand the calibration of our diagnostics. So that's to give you a kind of overview of our iron campaign, which used all of these different diagnostics and these targets. And at this time, I'm going to shift a little bit more into our main modeling approaches. So we have 2 main modeling approaches. We use a radiation hydrodynamics code called HYDRA, which we use a parametric heating source. We can base that off of target and laser parameters, and we can make assumptions or look at variations of things like opacity model, radiation transport, and electron conduction model. And from that, you can get out some output on the evolution of plasma conditions, and you can also post-process the results to get some type of simulated emission. For our other approach, we use also atomic kinetics and radiative transfer code and some radiation hydrodynamics. In Cretan, you can use it for that purpose, but we're using it for the atomic kinetics and radiation transfer. Cretan is a code that allows us to do that. And we usually do a simplified model where we just have kind of the single slab at a specific temperature and density. And we can look at a lot of different atomic physics parameters to put in things like atomic, time-dependent atomic kinetics, optical depth, line shapes, and also radiation transfer effects. And from Cretan, you can actually also get out things like simulated emission, but you can look more in depth at the ionization and the charge state distributions for the materials at the conditions that you've specified. So that lets us do a little bit more fidelity comparisons in a less time-consuming calculation. So for the 1D radiation hydrodynamics methodology that we use to do kind of general sensitivity studies, you can use it for sensitivity studies compared with data, or you can use it to kind of inform design. Sorry about that. Somebody has an echo. Thank you. So some of the design parameters you can change are things like laser energy, laser pulse shape, target dimensions, and you put that into the way we do the parametric heating in Hydra, which I'll describe a little bit more in depth in a couple slides. And you can also put in things like opacity model. Typically, we use the non-LTE atomic kinetics inline package, which you can run in an LTE versus a non-LTE mode, which we do pretty typically. We also can use different radiation transport methods, different electron conduction models, and we can analyze it. I use Yorick at the moment. So Yorick is actually an interpreted language. It's not its own necessarily code, but it has a lot of handy functions to read in hydro output. And one of them is a ray tracing that allows you to calculate the radiation transport through a user-specified ray that intersects the hydro mesh and uses the parameters on that mesh to calculate the radiation transport. And so by doing this kind of coupled process, you can look at how the change of your design parameter affects things like temperature, density, X-ray emission, and even opacity. Either you can look at the opacity directly from the model, or you can do kind of a mock-up of that opacity inference equation to see how it would affect the inferred opacity as well. And then you can do it as an iterative process to try to understand how sensitivities change these things overall. So I mentioned we use a parametric energy source. So this is to give you a little bit more context for what that means. With our hydro modeling, I mentioned it's a 1D geometry. And we're using this hydro DCA package, which is that inline atomic kinetics calculation. And when you do that, you actually rely on a super configuration based atomic model that you point to as the user. And so you can actually change that model and see if there's sensitivity to what type of configuration atomic model you're using in the calculation. Now, the energy source, as I mentioned, is simplified and parametric because we do not model the laser rays, and we do not model the hot electrons. Instead, what we do is we deposit an internal energy per unit mass uniformly in the target, and we make that energy source proportional to the laser pulse, and we do that through a conversion efficiency. On the right-hand side, I have a plot of an example 1D Gaussian pulse of that energy deposition source. So this is the power pulse. And the way that we connect it to the laser pulse is we set the full width half max of the Gaussian pulse equal to the full width half max of the laser, and we center the Gaussian far enough away from zero so that the majority of the, like over 99% of the energy is deposited when you use this type of source. So this is a Gaussian assumption in time. And we tune kind of the peak of this to some conversion efficiency from the total laser energy, which also feeds into how big the target is. So it's a energy per unit mass conversion. And so if you're interested in the details on the development and the verification and validation of this methodology, I have a paper from POP in 2017, which really outlines all those details and uses it for kind of an example design sensitivity study. So if you're interested in that paper, and you can always email me, I'll forward you the link to it, but I did put it on here for ease of reference. So in general, when we're modeling specific experiments, we actually tune that parametric energy source to reach a similar peak electron temperature that we infer from the specific experimental shot. So this is actually a figure taken from our milestone report where we have two different inferences from experiment. In the blue shade box, this is the inference of temperature from the sulfur K-shell streak using FlyCheck, and this was done by AWE. And then the white dots is the inference done here at Livermore using SCRAM, and there's a an uncertainty bar on that as well. And what I did is I tuned the peak temperature to be something kind of in the middle of these, and to see what type of energy deposition we need to do that. And so this is to kind of give us a bracket of a range of temperatures using this 1D methodology that is consistent with what we inferred from experiment. So this is how we use that conversion efficiency to tune to specific experiments, but I did want to talk a little bit more about how you can use this method to do sensitivity studies in an entirely simulated space. And one thing that we looked at was potentially adopting a different electron conduction model. So the baseline calculation for this 1D model uses the standard Lee and Moore. conduction, but we have looked at using a non-local thermal transport effect, and our kind of initial look at this during the milestone report indicated that it might improve some of our modeling, and so we should carry this forward as a potential sensitivity in the way we do this 1D model. So there's this non-locality parameter that's used to assess whether or not the non-local transport is important, and it's actually a ratio of the thermal collisional mean free path to the local temperature gradient length scale. And Hydra includes this non-local electron transport based off of this an extension of Skirtz, Nicolai, and Bousquet, which I've shortened to SNB here. And there's also the reference to this method at the bottom. And when you run our kind of the same energy deposition, same target, and you run it with the baseline versus the SNB, you do see that there is some early time for kind of first 10 picoseconds where the non-locality parameter is increased and above this kind of 10 to the negative 2 threshold area that suggests it may be important. And so what does this mean about our plasma evolution? So when we look at the average conditions in the iron sulfide buried layer, you can see that the peak average temperature is a little bit lower with the non-local transport. And so that's between the baseline and black. The solid line is our average, and the red is the S&B model. Solid line is average, dashed line is max and min. So the way we do that tuning might be sensitive to which choice of conduction model we use. And you also can tell from these comparisons that there is a wider range of conditions predicted by the non-local electron transport package. And so this might impact some of the plasma evolution and some of the spectra later. And so this was kind of a test problem we did as part of the milestone report, and we're looking at integrating this into our methodology as one potential sensitivity going forward in kind of our standard practice. Another thing I wanted to give you an idea for is how you can use this method to study sensitivities using simulated emission before you even compare them with experimental spectra. And so this comparison is actually looking at the difference between time-dependent and steady-state non-LT atomic kinetics. And so the reason we do this comparison is typically when we do the temperature inference using codes like SCRAM or even Cretan, we use steady state calculations to do those. And so this is one way to kind of look at, well, how does that impact our plasma evolution in this 1D rad hydro model? And so on the left-hand side is the average temperature, electron temperature in the iron layer. And you can see that the average condition is pretty similar. So there's not a whole lot of difference there. But if you look at the emission on the right-hand side, this is the emission at the time of peak electron temperature. So this is about 2 picoseconds. I've included the average sulfur charge state here just as reference. And this is the simulated emission about 1 degree from target normal, just barely off target normal. And you can see that there is a difference in the sulfur Lyman alpha between the time dependent and the steady state. And so this is driven by that slight increase in the sulfur charge state between the two models. And so we look at things like this to kind of understand what some of our assumptions in other areas might impact the emission that we measure. But ultimately, we want to use this to compare with experiment. And so here's a type of analysis we typically do. Is looking at assuming non-LTE versus LTE and looking at that compared to our actual experimental data. So on the left-hand side here, I have 2 models that both are tuned to peak at about 1.4 keV, which occurs about 2 picoseconds. But the blue one is assuming non-LTE and the red one is assuming LTE. And you can see that there's a qualitative difference in the average charge state predicted by this model in that iron sulfur buried layer. And if I do a simulated emission of our time integrated L shell measurement on the right hand side and overlay that with the data, the black is our HBS data, and then the blue is the simulated emission from non-LTE, and the red is a simulated emission from LTE. And you can see that it actually has reasonable agreement here on the L shell, with the caveat that there's some additional features here in the LTE calculation that's not represented in the data. So turns out the iron L shell in this case is not very sensitive to the assumption of LTE in our modeling. And when you look at the data, there's nothing particularly clear in this data that would suggest whether or not this is a non-LTE or not an LTE plasma. So I wanted to revisit this plot before I show you some more experimental comparisons, because I focused in on really trying to look at the difference between these two kind of peak temperature tuned models, the 1.1 keV model and the 1.4, and how does that compare with our time integrated data that we actually pull out of experiment. So here we have a comparison of the time integrated iron L shell on the left and the time integrated iron K shell on the right. And so you can see that the L shell is actually decently matched by both the lower temperature model and the higher temperature model. But on the K shell is very different depending between the two models. Even both of them actually kind of overpredict the iron K shell compared with data. So one thing to kind of bring up here is these are recent calculations that I revisited after our milestone report, because we found an error in our inline atomic kinetics calculation that was kind of undercounting the statistical weights assigned to transitions that populated a lot of our satellite lines, and you'll see that a little bit more clearly on the next slide. So we actually got better agreement with some of our satellite lines, but for the iron K shell, this discrepancy actually got larger, and so we're still trying to understand this a little bit better now, and what might be indicating, contributing to this discrepancy that we didn't see previously. So this is kind of work in progress. So here we have the comparison of the time integrated K-shell diagnostics, where this is the thing I wanted to point out. You can see the satellite features in the data on each of these K-shell lines. Well, originally when we started looking at this, we didn't see that from the output of the hydro model, and it was because of that update that was needed to the atomic kinetics calculation. And now we actually do see them in our modeling. So for the sulfur lines, you can kind of very clearly see even the high temperature case doesn't replicate the sulfur helium alpha and Lyman alpha, but it tends to overpredict for the chlorine and the potassium, whereas the lower temperature case is a little bit more consistent with the chlorine and the potassium. So you have kind of some range of temperatures that are contributing probably to different features in our spectra that we're measuring. So that's kind of a summary of the type of work we do with the 1D rad hydro modeling, but we also use Cretan to do more focused atomic physics sensitivity studies using 1D Cretan models, and we use those to compare with different spectral codes and also with data. And I'm going to kind of give you an example of how we've done that as part of our iron campaign analysis in the milestone report. So here we're using a fixed density, and we're looking at different electron temperatures from 0.8 to 1.4 keV. And we're using a 1D slab of just iron sulfide where we have the areal density conserved for that material. Typically, these are less expensive, and they definitely are not dependent on our assumed heating in the rad hydro because we're just fixing it conditions. Which makes them very convenient to kind of look at the more detailed atomic physics. And so with Cretan, you can run with and without radiation transfer. You can look at different treatments for optical depth effects, which the optical depth effects are approximated in the way we do the ray tracing from Hydra, but this approach allows us to do a little bit more rigor in that treatment. And we can also look at things like dependencies on assumed ion temperature. Again, I mentioned before you can get out from Cretan things like ionization, charge state distributions, and X-ray and simulated emission. Compare that with our measurement or different codes. So SCRAM was the one used for that temperature inference I showed previously. And then we also have another code called Enrico, which is a non-LTE code that we can simulate emission with and compare these three together. And we did that in the milestone report, although here in this talk, I won't be showing any of our Enrico calculations. So one thing we look at is including in radiation transfer and if that has an impact. So on the left-hand side, this is the average ionization for the iron and the sulfur. The red is without radiation transfer and the black is with radiation transfer. And so for the sulfur, which is that K-shell dopant we use to infer temperature, for the average ionization, it doesn't really have much of an impact. However, if you look at the dominant ion fractions, it does have an impact. So on the plot on the right, are with radiation transfer is the solid curves, and without are the dashed curves. And including radiation transfer changes which ion stages are contributing most in the assumption. And so this is one way to kind of look at, well, what's driving the emission and what type of ion populations are contributing. And so radiation transfer is something we think is there, and that's the more physical thing to assume. So using it kind of in this Cretan setup allows us to look at the difference if we don't use it for things like 0D models, which you can't include radiation transfer in, what impact might that have on the simulated emission? So here is a comparison of the iron K-shell with different Cretan models. Essentially, we are looking at the sensitivity of the iron K-shell to assumed temperature. On the left-hand side, we go from green and 1.2 keV all the way up to 1.8 in black. And you can see how it changes, increases the emission overall. Now this dip that we see in the Y line, that's actually an optical depth effect. And it's been a few slides, but you actually could see this in the post-processed Hydra output as well. There is that effect shows up there too as well. But if you compare it to the right, which is our actual OREX spectrum, we don't see that impact on the Y line here. So here you're kind of looking side by side to see what ratio between the W line and Y line might actually match best with the OREX. And the next slide will show that a little bit more clear, but it looks like from the ratio between the Y line and the W line, it might be right about that 1.8 keV. And so here on the left-hand side, we assumed that 1.8 keV, but we looked at changing the areal density of that buried layer to see if that impacts that optical depth effect. And since we didn't see the dip in the experiment, one way to get rid of that is to have a less optical depth in the target, which means lower areal density. And the one that matched the best is actually looking at about 15% of the nominal density of the target, where the nominal density is what we measured from the target metrology. And so it didn't really impact the Y line if you looked at these different thickness over nominal cases, but it did change that W line here. And so to zoom in even a little bit more here on the Y line, on the right-hand plot, we looked at the impact of the ion temperature on the Y line profile. And so looking at line profiles is something we can do with the Cretan, which is a lot simpler to do with these kind of focus calculations than it would be to do in a full rad hydro post-process framework. And the data is here in black. These are assuming an electron temperature of 1.8 keV, but two different ion temperatures. So if you tune the ion temperature down to about 1.2 keV in the red, you get a better match to the width of that Y line. And these also already assume that areal density of about 15% of nominal. So if you put it all together, you have a kind of hand-tuned match to our OREX data, where the simulation is black. I mean, the data is in black and our simulation is in red. And in this case, you kind of see that the ratio between the Y and the W line are pretty well matched, and the thickness of the width of the Y line is well matched as well. So these parameters were about 1.8 keV for the electron temperature, 1.2 keV for the ion temperature, and the areal density is 15% of nominal. So ultimately, we want to be able to bridge these two together as best we can. So these kind of standalone higher fidelity sensitive models with Cretan, but then also leverage them in our 1D rad hydro. And the way that we're approaching this is to couple the output of Hydra to Cretin and use Cretin to do the simulating of the X-ray emission, and then that way you can kind of change the different atomic physics included in Cretin and see how that impacts the emission, but use the heating profile from Hydra. And we're working on being able to parameterize the energy deposition not only in time, but also in space. So this would be including trying to approximate 2D effects that might be going on in these experiments. We'd use Hydra to get our plasma conditions, couple that to Cretin, and use Cretin to simulate all of the different diagnostics, those multiple signals we have, and then do a kind of a quantitative comparison between measured and synthetic data, and then iterate in a ensemble-based methodology to minimize some goodness of fit that characterizes that measured versus synthetic data, and constrain what type of assumed energy deposition we have to have in the targets to match the data for a specific shot or for a suite of shots. So that's the effort that we're working towards. And I've kind of just shown you one part of that and that work and what we did kind of mostly as part of this milestone report, but there's a lot of other work that's continuing and ongoing in the future. So for modeling and design, we have another FY22 campaign that we're using the kind of standard Hydra and Cretin models to do predictions and analysis of. I've mentioned that we're working on extending the Hydra model to include 2D effects, and I've also mentioned that we're looking to replace our ray tracing of Yorick using a post-processing of Cretin, using Cretin, and in that framework of trying to constrain the plasma evolution using measured and synthetic data. And that's actually being done by a postdoc I've been working with lately. And so we've, if you're going to be attending APS DPP, both Dylan, Rich, and myself will be presenting on some small focus of this work. So if you're interested, I would encourage you to tune in. But overall, our modeling and design effort is always focused on trying to improve understanding of sensitivities of our Orion platform using kind of the best things we have available and trying to improve them as we go. And this is at the same time that there's a lot of work being done by the experimental team focused on calibration of spectrometers, software development to ease data reduction and aid in kind of on-the-fly preliminary analysis while we're fielding campaigns, and also looking at other types of inference algorithms for inferring temperature from our measured spectra. And there's also an effort going on to improve, always improving diagnostics. And STOREX is actually a streaked OREX spectrometer that we're looking at fielding. And then we have our theory team that's constantly involved in all of our efforts to look at also predictions and analysis of our upcoming campaigns, working on improving our accuracy and convergence of our non-LTE code Enrico. And also there's an effort to generate non-LTE tables as part of an autonomous multi-scale SI, which this Orion team could leverage in the future. So we're trying, multiple fronts at the same time to best understand this platform and how we can use it to infer opacity. So with that, I'll leave up my summary slide and just kind of open the floor for verbal or handwritten questions.
Thank you very much, Madison. I'd like to give you a nice little round of applause and yay. Thank you for the talk. We've already got one question from Nathaniel Roth, who asks, in addition to feeding time-dependent Hydra output to Cretin, is there a plan to use the Cretin output to feed back into the Hydra evolution?
We aren't currently focused on that, although that's an interesting concept, and I think I haven't talked closely enough with Howard to understand the feasibility of that. But there has been in the past, especially with the emphasis from, I want to say like 2010, 2012 timeframe on fast igniter work, that there was a coupling done between Hydra and Zuma to do energy deposition based off that. And so that's also one way you could go about trying to enhance the way we do the energy deposition in Hydra. And so Zuma is a hybrid pick code, which you can do kind of hot electron transport in. So That's a good question. I don't know the feasibility of how we would do something similar using cretin, though.
And there's a question from Stephanie Hansen. Thank you for the fascinating talk. I'm curious about the finding of
TI
TI
less than
and
TE.
TE. Does that
So,
make sense with available estimates of electron-ion equilibration times?
one thing I forgot to mention about that is actually what Rich did that study, and it was very interesting because it was consistent with what is predicted by the 1D rad hydro. When I do the hydro models, I commonly see the ion temperature kind of lower and lagging behind. So like the peak electron temperature will happen at like 2 picoseconds, but the peak ion temperature will happen a little bit delayed, maybe like 2.5. It depends on the input parameters, and it's always a little bit lower. So it was interesting to see in that situation to see that kind of verification check with a different code, but assuming just a temperature distribution. So there is some type of ion-electron coupling that we assume in Hydra. What would be interesting is if we change that, how does that change the kind of trends I see with versus TE, TI, and the rad hydro? Um, I don't know specifically how the timing I see in rad hydro or the conditions Rich predicted with cretin, how that directly compares with existing electron ion equilibration times. I am not entirely sure. I guess I'd have to look at the data a little closer. But that's a good question. Definitely something of interest, and we don't infer an electron temperature typically from the data, so this is kind of an area for us to learn more.
Thank you. There's a question from Minsheng Wei. The inferred lower areal density seems to suggest the expansion of the heated microdot. Is that predicted in the Hydra simulations?
So for the 1D hydro simulations, we wouldn't see anything. I think you're talking about expansion in the radial direction. So that would be a 2D effect. So that's not at all addressed in any of the 1D hydra calculations. However, one thing that the lower areal density kind of suggests, it could be that maybe there's a smaller region of the areal of the microdot that's actually that high temperature and contributing to that iron K shell, which we might be able to mock up in a 2D sense with, maybe a peak somewhere in the way we do the 2D parameterization. We do think there is expansion in kind of the transverse. So this is like along into the dot. That expansion does happen, although it's largely tamped by the tamper. That's why we have the tamper there. And so I don't think that's the dominant effect. Of course, lower areal density, maybe one thing we thought is like, oh, well, maybe the initial density is lower than we think it is, but the metrology data is not really indicating that at all. So we're still got a question mark on what's driving the kind of lower areal density we need to match those iron K shell lines. And is that, if what we need to do that, is that consistent still with the sulfur, chlorine, and potassium lines that we're seeing?
So Rich had a comment to Nathaniel that cretin output might be used to choose the laser to hot electron efficiency insofar as the spectrum might indicate a different temperature than from Hydra by itself. And
Okay, that's a good point.
and then from Hai Lei, how well do we understand the heat source, i.e. hot electrons? Are there model data that justify the use of the parametric source?
Yeah, so I do cover that in my 2017 POP, and essentially with this parametric energy source, I was able to have similar results to the way these have been modeled by other codes that have some sort of hot electron transport in them. So this is kind of an approximation, but it's still verified similar conditions. I also did some modeling of previously published data and got similar peak temperatures, assuming kind of like a fixed energy source or fixed conversion energy. I think that with the heating source of hot electrons, there's existing data on like how many hot electron, like what type of hot electron spectrum escapes the target. We have data on the absorption of the short pulse laser on the front. And so that kind of puts a cap on how much energy you think actually got put into the target. There's a lot of additional experiments to try to better understand this heating mechanism, and I think that that's still kind of an open question. And there's a lot of different physics that people think might be contributing to some of this, and much of that isn't actually included in the parametric source. The handy thing with the parametric source is that it runs fairly quickly and you can do a lot of iterative design calculations, whereas trying to do like really well resolved and well um, uh, like strong, a lot of fidelity PIC simulations take a very, very long time. And that wouldn't be as useful for kind of quick iterative, like, well, what type of conditions will we reach and what type of emission signal will we see? And so that's what we've been mostly focused on. But certainly because we're really digging into data, we're interested in how we might better model these experiments for understanding our data overall.
And Minxing Wei has another question.
Time-dependent energy
Yeah,
deposition. Which
I think
energy conversion model did you use? I might ask you to come off mute and explain to me a little clearer what you mean by that. I literally, when I say conversion efficiency, it's literally like some percent of the energy of the assumed laser energy is deposited. So is there something else? I'm not sure if that's exactly the question you're asking.
Yeah, hey, it's very nice talk, fascinating. So yeah, this actually is about intensity dependent, kind of a energy conversion efficiency from laser to hot electrons, right?
Yes.
That I refers to. Yeah.
Yeah, so kind of like a Begg scaling.
Oh, I see. Yeah, but that back scaling was done for kind of like a 1 omega laser. So the intensity is it's kind of like it's quite different, in that scenario.
Yeah, so typically because I'm just assuming some energy deposition, usually the percent energy I've looked at like what amount of energy do I need to get similar conditions of this target, and they actually tend to be pretty consistent with um, either assumed energy conversion methods that have been done by other codes, or I think when I was looking at this with my previous design studies, so I hadn't done this exact calculation with this current campaign. I was getting, a few percents that were within the range of what I saw when I used the Begg scaling, but as you pointed out, that's 1 omega, not 2 omega light. So for the 1D parametric hydra, we're not using any type of specific conversion model. We're just putting some percent. It's not tied to another analytic form.
Yeah, the reason I asked that question is it's actually I know several Livermore colleagues, right? They've done comprehensive work, study that laser heating, including electron, kind of transport. So using LSP and coupled to hydra. I think Dave Strozzi did a lot of work on that. So I'm wondering whether you had any discussion with Dave about, incorporating source in transport for a better calculation.
Yeah, so actually, this has been several years now, but we did have a summer student, I don't know, maybe 2016 timeframe, that looked at trying to do, and it was a coupling between Zuma and Hydra, which was we were trying to build off of Dave Strozzi's work on that with the fast igniter. And that we didn't successfully couple those two codes for our application space at the time, and that didn't seem like a non-trivial. It was non-trivial to get that up and running, and was unclear if we would be able to have the assumed kind of refluxing hot electrons that we think are happening in the target with the Zuma capability. So we haven't put a lot of effort into that since. Largely, I moved on as I graduated in 2017, and I did something else for a few years, and now I'm back. But this is one of the things we're looking at trying to do as an improved energy coupling. I don't have a good quote for like how much longer it would take, but this seems like probably the best path forward for getting more accurate heating model still in a kind of way that might be iterative in like an ensemble approach.
Thank you.
You're welcome.
So Mahul Patel just had a comment about the time-dependent atomic kinetics and wanted to clarify that Cretan atomic kinetics is already inside Hydra. And then Farhat Beg had a question. There will be contribution in heating due to the reflection of hot electrons from the rear surface of the target. I know you are not running PIC. How do you accommodate this fraction in your calculations?
So we don't have a specific tuning to some assumed hot electric refluxing. Mainly, we're trying to capture that in the fact that that happens pretty quickly. Although actually I can go, let's go back. I want to put up this plot. You can see that the 1D rad hydro cools faster than the data predicts. And so in the past, what I've done is I've just kind of added on a low energy tail to get a better slope. There wasn't really anything empirical about that. I just added some low level tail on the Gaussian, and I could kind of match data cooling a little better, which maybe that would be a path forward for trying to figure out how to deal with the longer term impacts. But the refluxing hot electrons themselves are all captured in that conversion efficiency with the parametric heating. We're trying to mimic that with the assumed full with half max and the way that we assume deposit energy can tune from peak temperature to the model, from inferred peak temperature to the model itself. And when I do design studies, I usually fix that based off of, you know, some similar experiment that I tuned and then do design calculations. And so far for what we've been needing for pre-shots, that seems sufficient to try to get an idea of what type of emission we measure on our spectrometers.
Okay. Thank you very much, Madison, for the lovely talk. And thank you everybody for your questions and attending. We hope to see you all back next time. Let's thank our speaker again, and I hope you all have a great rest of your Thursday. Bye.
Thank you for the good questions, everyone. I really appreciate it. Thank you.